Welcome. Let's discuss the idea of sketching polynomials. To properly sketch a polynomial, we need to identify the solutions of that polynomial. And looking at the example that we have below, we can identify the solutions of this polynomial by letting the y value be equivalent to 0. And to be more specific, the solutions is whenever my graph intersects the x-axis. So let's do that. Let's look at this function and let's let the y be equal to 0. And now notice that on the right hand side, we are multiplying three expressions. The expression of x plus 3, the expression of x minus 2 raised to the second, and the expression of x plus 1 raised to the third. So to solve this equation, I'm going to let each of those expressions be an equivalent to 0. And now we can solve individually. Within the first equation that we have created, we can drop the parentheses, and then we can subtract 3. So now we have one solution, and that is when x equals -3. In the second equation that we have created, notice that we have an exponent of 2. So to get rid of that exponent of 2, let's start by taking the square root. That way the second exponent is going to cancel out, and the square root of 0 is 0, and now we got x minus 2, and by adding 2 to both sides, now we can say that x has a value of positive 2. But we have to be more specific than that. The solution came from an equation which had an exponent of 2. So we can say that the solution of x equals 2 appears 2 times, and we refer to this as multiplicity. We can say that the solution of x equals 2 has a multiplicity of a value of 2. Now, if we consider the third equation that we created, to solve for x, let's take the cube on the left and the right. That way the exponent is going to cancel out. And now we have that 0 is equal to x plus 1. And to solve for x, let's take away 1. But notice that the solution of x equals -1 came from an equation that had an exponent of 3. So we can say that the solution appears 3 times, but we're going to refer to that as having multiplicity of 3. So real quick, if we come back from the first one, the exponent was 1, so we can say that the solution of x equals -3 had a multiplicity of 1. So now let's see what would happen if we graph this polynomial. Let's see if the findings make sense. If we take a look at the value of x equals -3, notice that we have a solution. We are crossing the x-axis at the value of -3, and if we take a look at the value of 2, we are intersecting the x-axis at 2 as well. And the same goes with -1. But one thing to notice is that sometimes we actually cross the x-axis. Notice that we're going up to down. So we're essentially crossing the x-axis. And the same goes here. Notice that we're actually crossing the x-axis. But sometimes we do not cross the x-axis. We just barely touch it, and then we go up. When does that behavior occur? That behavior is predicted by the multiplicity of the solutions that we gather. At the solution of x equals -3, we said that the multiplicity was of a value of 1, which is of an odd value. At the solution of x equals 2, we said the multiplicity was of 2, which is an even value. And at the solution of -1, we had a multiplicity of 3, which it was odd. So notice that when the multiplicity was odd, at the value of -3 and the value of -1, we crossed the x-axis. And when the multiplicity was even, at the value of +2, we do not cross the x-axis, but we just intersect it, and then we bounce back. And that is a behavior that will always occur. And now to predict the end behaviors, notice that we can add the exponents of this polynomial. Here we're going to end up with a polynomial of degree 6, which is even. And based on what we have said previously about the leading coefficient test, here, if we add the exponents, we're going to have a polynomial of degree 6, and the leading coefficient is going to be positive because notice that there's no negative number on it. And based on what we have said before, if we have a polynomial of even degree with a positive leading coefficient, as we go to the left, we go up, and as we go to the right, we go up as well. So now we can combine these two ideas to sketch a polynomial. We can use the leading coefficient test to have an idea about the end behaviors, and then now we can use the solutions of an equation to predict what's happening between the end behavior. Let's take a look at one more example. So given the following polynomial, let's sketch it. The first thing that we want to do, let's identify the end behaviors. If we take a look at the leading term, we can see that the degree is even. And it seems like we do not have a leading coefficient, but there's an imaginary one in there. Notice that that's positive, then the leading coefficient is positive. So based on the leading coefficient test, if we have a polynomial with an even degree and a positive leading coefficient, we're going to be facing up on the left and up on the right. So now let's try to predict what's happening between those end behaviors. For that, let's try to find the solutions. Let's start by letting y be equal to 0. And now we need to start thinking of ways to rewrite the expression on the left. Well, one thing to notice is that on the left-hand side, every single term that we have there, they all have an x to the second in common. So let's factor that out. So let's just leave this x to the second as it is, and let's just concentrate on this trinomial. Notice that we can factor that out a little bit further. We're going to be looking for two numbers that if you multiply, it gives you a value of -2. And those two same numbers, if you add them up, they should give you a value of -1. But notice that those numbers are -2 and +1. So now we can factor out the right-hand side. Notice that we have 3 multiplications. So let's set each multiplication be equal to 0. And now let's solve each one of them independently. We can start by taking the square root of this. And now we can see that our first solution is of a value of 0. But we have to acknowledge that that solution came from an exponent raised to the second. So we're going to have multiplicity of 2. On the second solution, we can add 2 to both sides. But notice that this solution came from an expression which had an exponent of 1. So we can say that the multiplicity is 1. And lastly, let's take away 1 on both sides. And now we have our third solution. But this solution came from an exponent of 1. So we can say the multiplicity is also 1. So let's show that on our graph. So with this information, we can sketch our polynomial. Let's start by looking at the behavior from the left. So on the left-hand side, we're going up, and we're going to start decreasing until we get to the value of -1. But notice that at -1, my multiplicity was 1, which is of an odd number, so we will cross the x-axis. And we're going to decrease, and then we start going to go up until we get to 0. But once we hit 0, we acknowledge that the multiplicity was of a value of 2, which is even, so we're not going to cross the x-axis, or we're just going to touch it and then bounce. And then at some point, we need to start increasing, so we can go all the way to the value of +2. But notice that at a value of +2, the multiplicity was 1, which is odd, so we will cross the x-axis. And now notice that it matches the right-hand side behavior of this polynomial. We're going up as well. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.